Have you ever looked closely at a piece of cast iron? It's strong, it's heavy, and it's used to make everything from frying pans to engine blocks. But sometimes, things can go wrong when it's made. Imagine tiny hidden bubbles just beneath the surface. These are called pinhole defects. They are small round cavities that look like someone poked the metal with a pin while it was still soft. These aren't just cosmetic flaws, they are trapped gas bubbles that can weaken the final product. Understanding where these pesky bubbles come from is a fantastic journey into the science of chemistry and physics, all happening inside a super hot furnace. It's science. So, what's the big deal with a few tiny bubbles? Well, in the world of engineering, even small imperfections can lead to big problems. These pinholes are stress concentrators. That's a fancy way of saying they create weak spots where cracks can start to form, especially when the cast iron part is under pressure or strain. Think about a car's engine block. It has to handle intense heat and pressure. If it has pinholes, it could fail. Uncovering the mystery of these defects is crucial for making reliable, safe, and high-quality cast iron products that we depend on every single day. It's all about controlling the gas. The main source of these troublesome bubbles is gas dissolved in the molten iron. The most common culprit is hydrogen. Where does this hydrogen come from? Often, it comes from a very simple and common molecule, water, or H2O. When even a tiny bit of moisture comes into contact with scorching hot liquid metal, which can be over 1400 degrees Celsius, that's 2500 degrees Fahrenheit, the water molecule violently splits apart. This reaction frees up hydrogen atoms, which are so small they can easily dissolve right into the molten iron, just like sugar dissolves in your tea. But this dissolved gas doesn't want to stay there forever. This process is a classic example of a chemical reaction driven by extreme heat. The liquid iron is so energetic that it eagerly breaks down water and other compounds it touches. The result is a liquid metal soup filled with dissolved gases, patiently waiting for their chance to escape. As we pour this molten metal into a mold, we set the stage for a dramatic race against time. Will the gas get out before the metal solidifies and traps it? The answer to that question determines whether we get a solid, strong casting or one riddled with hidden pinholes. Let's consider this. Hydrogen is the primary troublemaker, but it's not working alone. Nitrogen is another gas that loves to cause pinholes. Nitrogen is all around us. In fact, it makes up about 78% of the air we breathe. Normally, it doesn't bother molten iron much. However, certain elements added to the iron can act like a welcoming committee for nitrogen, encouraging it to dissolve into the metal. These elements are what we call alloying elements, and they are added to give the cast iron specific properties. But sometimes they have unintended consequences, like rolling out the red carpet for unwanted gas atoms. Let's talk about those elements. Aluminum and titanium are two big ones. When they are present in the molten iron, even in very small amounts, they can react with nitrogen from the air. This reaction makes it much easier for nitrogen to get into the metal solution. Think of it like this. Aluminum and titanium open the door for nitrogen to come inside and hide. Magnesium, another element often added to make a special type of cast iron called ductile iron, can also increase the risk of hydrogen-related pinholes. These elements are helpful for some reasons, but can make the gas problem much worse. So now we have a molten metal bath filled with dissolved hydrogen and nitrogen. These gases are just floating around, invisible to the naked eye. The problem is, hot liquid metal can hold a lot more dissolved gas than cold solid metal can. It's like a warm can of soda. It can hold a lot of fizz, but as the metal begins to cool down after being poured into a mold, its ability to keep these gases dissolved drops dramatically. The gases are suddenly being kicked out of the solution, and they start looking for a way to escape. They want out. This is where the bubbles start to form. The hydrogen atoms find each other and team up to form hydrogen gas, H2. The nitrogen atoms do the same. They gather together, creating tiny pockets of gas within the cooling liquid. If the conditions are just right, or from a manufacturing perspective, just wrong, these pockets of gas will grow. They are the seeds of the pinholes we see in the final casting. The presence of elements like aluminum and titanium essentially supercharges this bubble-forming process, making it much more likely to happen. Now, let's move from the metal itself to its temporary home, the sand mold. Most cast iron parts are made by pouring liquid metal into a mold made of tightly packed sand. But this sand can be a major source of the very moisture we are trying to avoid. If the molding sand is too wet, you have a recipe for disaster. When the ferociously hot iron hits this damp sand, that moisture instantly turns into steam. This steam explosion creates a huge amount of hydrogen gas right at the surface of the casting, which is the worst possible place for it to be. The properties of the sand itself are also incredibly important. Sand grains need to be packed together in a way that allows gases to escape. This property is called permeability. If the sand is packed too densely, or if the grains are too fine, the permeability will be low. This means that any gases produced, whether from moisture or from the binders holding the sand together, get trapped. They can't vent out through the sand, so their only option is to push back into the liquid metal, forming bubbles right at the mold metal interface. Poor venting is like putting a cork on a boiling kettle. Let's not forget about the binders and cores. Binders are like the glue that holds the sand grains together to form a strong mold. Cores are hard sand inserts used to create hollow sections inside the casting. Many of these binders are organic, carbon-based materials. When exposed to the intense heat of the molten iron, they decompose and release large volumes of gas. If these gases cannot escape through the sand quickly enough due to low permeability or poor venting design, they will force their way into the casting, creating pinholes. It's a constant battle to let the good stuff, metal, in and the bad stuff, gas, out. Finally, the way we melt and pour the iron matters immensely. During melting, a layer of impurities called slag forms on top of the liquid metal. If this slag gets mixed into the iron during pouring, it can be a source of gas-forming reactions. Furthermore, pouring the metal too aggressively creates turbulence. This violent splashing and tumbling action folds air into the metal. Just like when you are mixing a cake batter, this trapped air introduces both oxygen and nitrogen, adding even more gas that needs to be dealt with. A smooth, calm pour is essential to keep extra gas out. We have all the ingredients for pinholes: a liquid metal full of dissolved gases, a mold that might be adding more gas, and a pouring process that can stir things up. The final act of this scientific drama happens as the iron cools and solidifies. As we touched on earlier, the solubility of gases like hydrogen and nitrogen in iron drops sharply as the temperature falls. Think of a soda going flat as it warms up. This is the opposite. The metal is going flat as it cools down, releasing its dissolved gases. The party is over for the gas atoms and they are being kicked out. This sudden release of gas is what forms the bubbles. But where do they form? Often they form right at the boundary where the metal is starting to solidify. As the outer layer of the casting cools against the cold sand mold, it begins to form a solid skin. The dissolved gases in the remaining liquid metal nearby are rejected from this solidifying front. They get pushed ahead of the advancing wall of solid iron, concentrating in the liquid that's left. This concentration can become so high that the gases spontaneously form bubbles, like the fizz in a freshly opened soda bottle. These newly formed bubbles are light and they want to rise to the surface and escape. However, they are in a race against the clock. The metal is cooling and thickening rapidly, turning from a thin liquid into a thick, syrupy slush. This mushy zone makes it very difficult for the tiny bubbles to move. They get stuck in the thickening metal like a fly caught in honey. The solidifying skin of the casting advances from the outside in, and it quickly traps these bubbles in place before they have a chance to float away. They are frozen in time, just beneath the surface. And there you have it. That's the story of a pinhole. It begins with gases like hydrogen and nitrogen dissolving into super-hot liquid iron, a process often made worse by moisture, certain alloys, and binders in the sand mold. As the iron is poured and begins to cool, its ability to hold these gases plummets. The gases come out of solution, forming tiny bubbles. Before these bubbles can escape, the rapidly solidifying metal traps them in place, creating the small, round defects that can compromise the strength and integrity of the final cast iron part. Science, it's all about controlling the gas. Well, guys, don't forget to subscribe my channel and let's go back to Foundry jobs.